I've been trying to figure out, how I would, because I got a bunch of stepper motors and I've been harvesting out of various equipment. But, I really don't know much about any of them. The only one I actually know anything about, um, is this one here, which I bought, off Amazon. And if you can trust the readings of the dubious manufacturer, well, then, yeah, I mean, this has a known load profile to it. But none of these other motors, most of these, I mean, I've tried to look in half a dozen or more of these things up, and I can't find any data sheets on them whatsoever. And some of these are unipolar, and some of them are bipolar motors. But a lot of these don't even have, like the torque published. A few of them do. Um, let's see. I think, well, maybe, that one doesn't. Let's see. What the hell was one of those that did? Well, anyway, I had a couple of them that did, and they came out to like 53 ounce inches at a certain voltage, and like I said, I'm still actually trying to understand the specifications behind a stepper motor. Man, this phone isn't so great. But like this little motor here, um, you can see it's a 7.5 degree step, but it's 2.8 amps per phase. But again, at that level, I find it has 2.3 ohms of resistance, and it would be approximately 6-volt motor to get that. Let's see, whereas like this one, it's 28 volts and 53 ohm motor, so if you're running at 12 volts, it'd be half that. But some of these motors, say they're 5 volt, but I mean, I don't see why you couldn't run it at like 12 volts. Now it might overheat, because of the additional current and so forth, but it looks like you could put some current limitations on that and still get the benefit of a higher voltage. But that remains to be seen. But anyway, the whole reason I'm making this video is I'm trying to keep a couple of ideas I had for the possibility of actually profiling stepper motor, unknown stepper motors, I should say. Because you can get, basically these sorts of curves. That's interesting. It's a strange profile. Anyway, I kind of look at these curves on these stepper motors from this arbitrary company I found that they published, full specifications on their motors. I'm just trying to, kind of understand, well, okay, how do they come up with these specifications? So, because again, you see, loading curves like this, but they're, clearly empirical measurements, I would say. So, how do they come up with this? These types of load curves. They're dynamic load curves. You got your, damn it, your pull-in torque and all that stuff, plotted on here, and as well as the dynamic torque. But it occurs to me that there's probably a couple ways you can measure it. It seems like if you had an apparatus where, like, if you had like a threaded rod, okay, that sticks out, um, damn it, anyway, sticks out, that you had attached to that shaft in the middle of that threaded rod, you had it affixed to the shaft, and on that threaded rod, if you were to put two adjustable weights, okay, so you could adjust the rotational inertia of that rod, well, then that rotational inertia will give you an indication for any setting. Again, you adjust the two weights, one on either side of the rod, so that you can either start, the closer to the center you are, the smaller the rotational inertia, whereas the more towards the edge you are, say the rod was like 2 feet wide, right? So if you put the weights out at either end, to the very maximum level, that will give you the maximum rotational inertia. And again, as you know move the weights more towards the center, that decreases the rotational inertia. Anyway, that gives you a known quantity that you can calculate, and then if you actually, basically applied a pulse train, starting with the highest rotational inertia, in other words, the weights at the extreme ends of the rod, that's where you start. You apply a pulse train, and you keep increasing the pulse until the motor starts skipping steps. And at that point, you theoretically could calculate what torque you're applying, for that given rotational inertia. Because again, the higher your rotational inertia, the more of a torque challenge that's going to be to a motor that you're trying to ramp up to a given speed. So it just seems to me that, again, with a little bit of mathematics, you could, kind of figure, okay, for a given rotational inertia, what speed is step speed, pulses per second or whatnot, is it as it's starting to skip steps at. Okay, then you make note of that on your, have a computer or something, record that value, and then you stop the apparatus, okay, and adjust the weights inward a little bit, and say, okay, well, I'm calculating this rotational inertia for this, so let's start it up and find out what pulse limit it tops out at. Every time you move those weights toward the center, the pulse, the number of pulses per second should increase, because the rotational inertia is decreasing. So, in other words, you should get an ever decreasing amount of torque at an ever increasing, amount or number of steps per second. So that should give you an actual profile, at least till the point that the motor starts to skip steps, which I think these kinds of curves are actually based on. It's that threshold, between controlling the motor and not controlling the motor is what I think that means. But at any rate, that's an apparatus. Of course, it'd be a little time consuming, but you could do 10 or 15 steps on that, to figure out, to take 10 or 15 data points, and that should be able to interpolate a graph, maybe not as precise as that, but close to it. But it also occurs to me that another possible measurement apparatus is if you actually had a force gauge, you could actually hook it to, like, okay, you put like a 1-inch radius wheel on it, for example, if you want to get ounce inches. Okay, and then you pull a string off that and you attach it to a strain gauge, right? So, but basically, the theory is that every time you apply a pulse, it'll stall the motor out. This will be a stalled motor measurement, but it certainly occurs to me that every time it tries to step, it'll generate a little impulse, in that, a little bit of torque impulse, but otherwise it'll be static. Like, for example, if it was trying to, you're applying like 1 pulse per second, for example. Well, for one really small fraction of a second, you get a torque impulse, but then the rest of it would be just a static measurement. Remember, we'd have a strain gauge attached to it, but it's a static apparatus, so it's not actually pulling on it unless the motor is actually pulling against the gauge. But otherwise, the gauge is just sitting there. So if you weren't actually trying to apply any pulses, the reading would be 0. Because it's just a static apparatus. The only time it would ever give you a reading is if the motor was trying to turn but not being able to. So in other words, every reading you take would be a failed step. But the point is that in theory, that still should represent, maybe a torque that represents, what the average, what the actual torque at a given speed might be. And then again, as you increase the pulse train, what you'd have to do though is you'd have to set this up with like a voltage divider and put it on an oscilloscope, because you're looking for whatever that peak curve is. And in theory, as your pulse rate increases, the magnitude of that curve should drop. In other words, you should see essentially a lower and lower torque pulse, as your speed increases. Now, I mean, it seems plausible, you know, and again, you might have to do some adjustments in the numbers, you know, but again, you have a computer record all these data points and apply these pulses, and, you know, theoretically, it may be, you know, it may be a good indication of what the torque is to try to generate a load profile, a load curve. I'm not sure if it would work or not, but I mean, it seems plausible. Um, but again, you know, because again, you know, you can figure, you know, that as the the pulse train increases, you know, again, the field at some point, you know, won't be, you know, able to fully collapse before another field comes in. So, but the result would be is, you know, lowered load torque on a lower load curve, you know, on your meter as the pulse train increases. So again, in theory, you know, you'll see that diminished torque, you know, to get some kind of a curve like that. So, but again, the motor itself is actually not spinning. It's trying to spin, but it can't. So again, I don't know how, you know, valid of a theory that is, but you know, it's just a couple of ideas that might be worth trying. Anyway,